I want to mention briefly one other model that is commonly used for BJTs, and that is H parameters. So the reason I want to mention this H parameter model for small signal analysis is because this is typically what you'll see on data sheets, these H parameters. So typically on data sheets. And so I've got sort of our small signal equivalent circuit drawn here. So note this is for an NPN transistor. Again, we could easily adjust things to make it for a PNP like we saw for our hybrid pi model in the previous video. But from looking at this, we can look at our input loop and our output loop, and we can write equations relating relevant voltages to currents. And again, before I do that, let me just explicitly write, we've got, of course, our base over here on the top left, our emitter in the bottom, and our collector over here on the top right. So we could say that our base emitter voltage is equal to HIE times our base current plus HRE times that VCE. And then our second equation would be IC, so looking on the right side, is equal to HFE times IB plus HOE times VCE. And so again, the four sort of H parameters are then HIE, HRE, HFE, and HOE, and we see them appearing in the equivalent circuit in the areas highlighted above. And so we can relate these back to our hybrid pi parameters as well. And so we can do that by saying, well, our HIE is this series resistance over here at the input to our base terminal. So primarily that's going to be our R pi, our diffusion resistance, but to be more complete, what we can say is that HIE is equal to, remember we said there's that RB, that really small value of our base resistance, plus our R pi in parallel with that R mu, which we said was really large, typically mega ohms. So if that's true, the R pi dominates that parallel connection, yet it's still larger than the RB, so we say that this HIE is approximately our diffusion resistance R pi. The next parameter sort of on that input side is that HRE term. And so what we can see is this is adding some dependence in our input loop on that output voltage VCE. And so I'm using input and output pretty loosely. Of course, it is ultimately determined on how our circuit is configured that our BJT is in. But if we look at that other parameter from our input loop, the HRE, essentially it's relating, like I said, that the VCE to the input side. So that's also going to be related to that that R mu, which connects the base to the collector. And so what we would see is that that's actually equal to R pi divided by R pi plus R mu. And so because that R mu value is so large, this is usually approximately 0. And that's kind of what we said in our hybrid pi model is, let's say that this doesn't really depend on the VCE, and we just had sort of a short circuit there. So we just had the one R pi resistor. So now for the two H parameters on the output side, we have our HFE, which we notice we have IC equals HFE IB. And so we can see from that that our HFE is just going to be equal to GM R pi, which, as we said previously, is equal to beta. And so typically this is going to be the most useful or most important one. Oftentimes this is what we'll be going to find on data sheets. You won't see the beta, but instead oftentimes on data sheets what you'll see is an HFE parameter. And so it's useful to know, of course, that those are the same things. And so you can look in the textbook for some more information on data sheets. So if you look on pages 391 to 396, you can see some more information on that, as well as some sample data sheets where you can actually see this HFE parameter given. And then finally, just for completeness, we can say that HOE parameter, obviously that's relating to our early effect over here on our collector side. And we can define that as saying that, well, that's approximately just 1 over that small signal output resistance that we defined previously.